Chapter 8. Jefferson Wheel Cypher. This chapter covers Thomas Jefferson's wheel cipher, solving a wheel cipher using a known word, solving a wheel cipher when no words are known. Thomas Jefferson invented the Jefferson wheel cipher sometime between 1790 and 1793 while he was serving as Secretary of State to George Washington. The device consists of an iron rod or spindle 1/8 to 1/4 inch in diameter and 6 to 8 inches long, with 36 wooden discs about 2 inches in diameter and 1/6 of an inch thick. Each disc has a hole drilled through its centre the same size as the rod, so that all of the discs can be placed snugly onto the rod, forming a wooden cylinder. The flat faces of the discs touch one another, with the outside rounded edges visible. One end of the rod has a head, like a nail head. The other end has screw threads so that a nut can be screwed onto the rod, holding the discs firmly in place. The discs are numbered from 1 to 36 on their flat sides. The round outer edge is divided into 26 equal sections. The 26 letters of the alphabet are written or incised into these 26 sections in some scrambled order, which is different for each disc. The order of the discs on the spindle is the key for the cipher, which is nowadays called a multiplex cipher. Here is a reproduction of a 26-disc Jefferson cipher wheel displayed at the National Cryptologic Museum in Fort Meade, Maryland. Photo courtesy of Dadero, under the Creative Commons CC 01.0 license. A message is enciphered with this device by first placing the discs on the spindle in the order specified by the key. The nut is screwed on loosely so the individual discs can be turned. The first letter of the message is found on the first disc, and the second disc is turned so that the second letter of the message is next to the first letter. Then the third disc is turned so the third letter of the message is next to the second letter, and so forth, until the first 36 letters of the message are lined up in an even row. The nut is then tightened to keep them in place. Turning the cylinder, there are 25 other rows of letters, all of which are meaningless jumbles. Sandra may choose any one of these as the ciphertext. Reva repeats this process, setting up the ciphertext on one row of the cylinder. It will be obvious which of the 25 other rows is the intended message. Jefferson apparently never put this cipher into use. The concept lay dormant until it was reinvented by Etienne Bazary in the early 1890s. It was adopted by the French in 1901. Bazary's version had two improvements. It had a stand or cradle so the device could be placed on a desk for two-handed operation, and it had a guide that helped the user line up the letters evenly and select the row for reading out the ciphertext. A version of this cipher using 26 aluminium discs was invented by Colonel Parker Hitt in 1914 and adopted by the U.S. Army in 1922 as the M94 and by the U.S. Navy in 1926 as the CSP-488. Hitt's version was only 4.25 inches long, small enough to fit in a pocket, and had notches and prongs on the flat faces of the discs that kept them from slipping after they had been aligned. Here is a photo of the CSP-488 from the National Cryptologic Museum. A flat version of the cipher was invented by Hitt in 1916 and adopted by the Army in 1935 as the M138. This version was a flat aluminium board with 25 channels that held paper strips that could slide back and forth to simulate the turning of the discs. Each strip had 2 copies of the scrambled alphabet. This device was more secure, since the paper strips could easily be replaced and even handwritten in the field if necessary. This was soon replaced by the M138A or CSP-845 in the Navy, which had slots for 30 paper strips. 100 strips were supplied with the device, designated by 2-digit numbers, so any message used 30 out of 100 possible strips. This allows for 100 factorial over 70 factorial, which equals 7.79 times 10 to the power 57 possible keys. The M138A had a hinge in the centre so that it could be folded for easier carrying. Each half had a separate guide that was used for aligning the strips and reading out 15 letters of the cipher. These improvements considerably strengthened the cipher. These strip ciphers were dropped by the Army around 1942 or 1943, but they remained in use by the Navy as a standby in case of a loss of electrical power makes it impossible to use any of their electronic or electromechanical cipher devices. It is not feasible to solve a multiplex cipher if Emily does not have a copy of the device and does not know the alphabets. If Emily possesses the device, the cipher is relatively easy to solve if she knows some probable words. When Emily possesses a copy of the device and knows some probable words, the Jefferson cipher wheel is rated 4 to 5. When no probable words are known, the rating is 6 to 7. The more ciphertext Emily has, the lower the rating. Conversely, if the device has lots of extra disks, the rating goes up. For example, if the device holds 30 disks that the user selects from a supply of 100 disks, the rating can go to 8. For very short messages, less than 2 times the number of disks, solution may be impossible unless Emily intercepts multiple messages using the same key. This may happen if the sender changes the order of the disks only once per day. Section 8.1. Known word solution. You can solve a message enciphered with the Jefferson cipher wheel when you have enough text and you know at least part of the message. Often, just a single known word is sufficient. Suppose you know that Sandra is using the M94 device, which has 25 disks, and you have intercepted a message. Suppose you also know the plain text message begins urgent. This has been transformed into the ciphertext CLPOXF. Since urgent is on one row and CLPOXF is on another row, the distance between corresponding pairs of letters must be the same. Let's call the row with urgent row 1, and suppose the row with CLPOXF is row 8. The first letter of the plain text U and the first letter of the ciphertext C are taken from row 1 and row 8 of the first disk. So, on the first disk, the distance from U to C must be 7. On the second disk, the distance from R to L must be 7. On the third disk, the distance from G to P must be 7, as well as E to O, N to X, and T to F. The easiest way to search is to try each possible distance from 1 through 25 in turn. Start with distance 1. Find all of the disks where the distance from U to C is 1. In other words, where the next letter after U is C. If there are no such disks, then you know the distance is not 1. Then find all the disks where the distance from R to L is 1. Again, if there are none, the distance cannot be 1. Let's suppose that you have found 12 sets of disks where the letter pairs are all at a distance of 1. You now need to test these 12 sets to see if any of them are correct. Let the first set of disks be, say, 18, 4, 21, 9, 13, 11. Start testing with the second block of the ciphertext, letters 26 through 50. This block starts ESIWVI. Set disk 18 to letter E, disk 4 to letter S, disk 21 to letter I, and so on. Now look at the other 25 rows. If they are all gibberish, like HNSAEI or TFPGUW, then you know 18, 4, 21, 9, 13, 11 is not the correct sequence of disks. On the other hand, If you see some plausible text like NCONDI, which could be part of the word unconditional, then 18, 4, 21, 9, 13, 11 might be the correct sequence of disks. Test again using the third block of the ciphertext, starting with GAFOEM. If the third and fourth blocks all lead to reasonable text segments, then 18, 4, 21, 9, 13, 11 is probably correct. But keep searching because you might find better disk sequences. If you don't see any likely snippets of text, then try the other 11 disk sequences. If none of these work, try distance 2, then distance 3, through distance 25. There will probably be a few hundred combinations of disk order and distance to test. This is tedious, but still feasible by hand. If nothing works, go back and look for disk sequences where 2 out of the 3 tests give plausible text. Once you have settled on the most probable sequence for the first 6 disks and the corresponding distances, then you try to extend this to the 7th disk. For each choice of disk you already know the distance from the plain text to the ciphertext, so the extension process goes fairly quickly.